Okay, so we are going to start your quadratics review for your exam, and I'm going to jump all over the place because there's 3 pages, and so it's a very large review packet, but it's our power standard, so it's the one that we covered a lot. So um, we're going to start off with a little bit of factoring, solving. We're going to solve using Desmos. We're going to look at graphs and key features of graphs. We're going to look at regression, all of those things um, using Desmos. So let's start off first with kind of reviewing what factoring is. The first thing that we're going to look at is factoring out a GCF. So remember that GCF is greatest common factor. So we're looking at the numbers 21 and 12. And we're going to look for the largest value that can be divided into both. And so when we did this, we took 21 and we started breaking it down into its prime factors. So the only thing that multiplies to 21 is 3 and 7. For 12, it could be 2 and 6. I could have chosen 3 and 4. The 2 cannot be broken down, but the 6 can be broken down again into 2 and 3. And since greatest common factor is the most that they have in common, I start looking for what numbers in my factor tree do they have in common. And I see they both have the number 3. They don't share any variables. And so my GCF is 3. Now, when I was kind of playing around the other day in Desmos, I discovered that you can actually have Desmos find the GCF for you. So let me see if I can pull up Desmos. So in Desmos, if you go in here, you can go to your keyboard in Desmos, and there is the ability to find a GCF. So what you have to do is when you have this open, you simply type in GCF, so GCF, and open parentheses. Okay. What you're going to do is type in the two numbers that you're looking for the GCF. So for in this example, the numbers was 21, comma, and 12. You can see here the GCF is 3. So that's one way to help you if you're struggling. I did not know this existed until the other day when I was just kind of playing around in it. Um, if we wanted to use Desmos to help with another example, let me see if I can move this. Let's look at this one. We have, let's look at like number 3, the GCF between 75 and 30. If I'm looking for just numbers, could come in here and say um, 75 comma 30, and I can see that the GCF is 15, and then all I have to worry about is like their variables and things like that. So if I wanted to pick up on that example, I would say, okay, well, I know that my GCF was 15. They share one A because there's 2 of them here, 3 B's and a C. This is an A and a B and a B. So they share one A. They share 2 B's, and so my GCF is 15AB squared, and then it's just whatever's left over. So 75 divided by 15 is 5. I had one A and a C left over, and here I didn't have anything, so it would just be a 2. You do not have to know the difference of 2 squares because you can factor these the same way that we did anything else by simply saying, okay, there's no middle term, so let me put a 0 and then factor like normal. Or there's no middle term, let me factor like normal. So you're like, what is factoring by normal? That's those regular trinomials that look something like this, where you have to break them down into their 2 parentheses or their 2 factors. And so our process was to take your front number, in this case a 1, and multiply it to your last number. So 1 times 30 was 30. And then you're going to list out all those factors of 30. 1 times 30, 2 and 15, 3 and 10, 5 and 6. So all of the numbers that multiply to make 30. So you're going to look for a set a set of 30 that add up to make the number negative 13. I know that 3 plus 10 is positive 13, and I still have to add them. So I can say a negative 3 and a negative 10 should, oops, I've left out my p. There we go. Should still add up to make a grand total of negative 13p. So we're not changing the value, we're just changing what it looks like. So we drop the front, we drop the back, and now you have 4 terms. And even though we have more terms, it's actually easier to factor because we split them down the middle. You find the GCF of the first two. So p squared minus 3p, they both share the value p. So if I divide a p from both of them, I'm left with a p minus 3. We drop that sign comes straight down. And then I do the same thing. What's the greatest common factor between 10 and 30? The answer is 10. And then I divide each one of those terms by negative 10. So this leaves me with a p. And 30 divided by negative 10 is negative 3. And I know I factored this the right way because we have a set of twins. So when we were learning this in class, we would say twins in the front and your junk in the trunk. And this is called your factored form. If I wanted to double check that this is correct, I could absolutely use Desmos. So I could come in and graph it. So y equals, oops, not y squared. Y equals, and instead of a p, I'm going to use an x. So x squared minus 13x plus 30. Make this a little bit bolder so we could see it. So here's my graph. And if I factored correctly, if I graph those sets of parentheses together, x minus 3 times x minus 10, I should get the exact same graph. And you can see the red has turned to blue. They're the exact same graph. And so that would be considered the factored form. If I was taking my final exam and I did not know how to factor, I would start by putting in my equation, my original equation, and then start putting in your answer choices until you have a graph that matches. And so the same process works if we are going to factor something that doesn't start with the number 1. So here, we're same process. We're going to take that first number 3, multiply it to the last number 3. So 3 times 3 is 9. And the only two numbers that multiply to 9 are 3 and 3, or 1 and 9. So if I'm looking at this, I'm looking at pairs of numbers that add to make a 10. Well, I know 1 plus 9 is 10. So I can break that 10x into a positive 1x and a positive 9x, bringing down the things that I have not used. I have 4 terms, so I can split them down the middle and then find the GCF of both sides. So the GCF of 3x squared plus 1x is just the value x, leaving me a 3x plus 1. And the rule is always to drop that sign, no matter what. That way we don't lose negative signs. The GCF between 9 and 3 is the number 3. If I divide a 3 out from everything, I'm left with 3x plus 1. There's my twins in the front, and my junk in the trunk. And there's your factored form. You could check it in Desmos if you wanted to. So if I come in here, let me change these. So if I come in here, I can put in my original equation. So 3x squared plus 10x plus 3. That's the red one. And put in my 2 factors that we found. Or if it was an answer choice on a test and I didn't know what to do, I'd just start putting answer choices in, playing the matching game. So x plus 3, close parentheses. And we turn this one back on. You have a red and you have a blue. And you can see that these are the exact same graph. And so we know that we either factored correctly or we found the correct answer. So all of those shapes have been something called a parabola. And so this is the kind of shape that you have to find at your house for your final project. But remember that this parabola has 5 main features that we have to be able to identify, kind of identify in context. We have the big popular ones, which are like your y, where it intersects the y axis. This is called your y-intercept. You have the lowest or highest point on your graph. That is referred to as your vertex. If it's at the very top of your graph, it's a maximum. If it's at the very bottom of your graph, it's a minimum. This blue dashed line that cuts the graph in half, goes right through the vertex. This is what we call our axis of symmetry. And so remember, the word symmetrical or symmetry means to cut in half. So that's what it does. And then the last ones are your 2 points here. They have 4 names. They can be referred to as your x-intercepts. They can be referred to as your roots. Most of the time we will call them zeros or solutions. And you can find those right in the graphs from Desmos, or sometimes we just have to kind of interpret them based off of like what the question is asking. All parabolas can be written in one of 2 forms. You can have your standard form, which is just ax squared plus bx plus c is equal to y, or y equals that. A, b, and c are just numbers. So for example, they look like number 10, 3x squared plus 10x plus 3. Or you can have it written in vertex form, which is a times x minus b squared plus, oops, let me take that back, because we learned it as h and k, where the vertex is located at hk. And this is where we talked about like h is a liar and k is kind. So you have to look at h, look at the sign. The sign is a lie. So, if it's a plus sign, it looks like it's supposed to go to the right, but it's a liar. So it goes to the left, but k is very kind. It will tell the truth. So here we go. I'm going to graph these in Desmos, and then I'm going to come and look at these key features. Okay, so I have my Desmos up, and I'm going to graph this equation. So x squared minus 6x plus 8. So here's my graph. Make it bold so we can see it. And on your graph, you can identify all of these key features. So just click on the graph. You can find your y-intercept. You can find your vertex. And you can also find your solutions or your roots. If you need to make a table, you can come in here, you can click on the settings bar, you can turn it into a table. You can see all of those values. You can plug in a value for x, kind of see what your y value would be, so it'll do all the math for you. But these key features on the right-hand side are asking you for domain, range, axis of symmetry, your vertex, x, and y intercepts. And so if I was looking at my graph, I would say, okay, well, my y-intercept here is 0, 8. So I didn't have to do anything. I just kind of had to look at my graph. My x-intercepts are where that touches the x-axis. So I don't need my y-intercept anymore. So my x-intercepts or my solutions would be 2, 0 and 4, 0 because the graph touches twice. Slide this over just a little bit. My vertex, that's kind of the top or bottom of my graph. So my vertex is located at 3, -1. And the axis of symmetry has to go directly through the middle of my graph. And so that's going to be the equation x is equal to 3, and that comes from your vertex. Now, the thing that we struggle with is domain and range. Domain means from your left all the way to your right. So we look at the graph and we say, okay, what's the farthest to the left that this graph will go? So we come in Desmos and you can drag your graph and you can see that even though you keep going, that graph never, ever, ever stops going to the left. And the same is true on the right. It never stops going. If you zoom out, you can see it keeps going forever and ever and ever. And so we say, because this goes forever and ever, all real numbers. Any number that you can possibly think of, if it's a real number, it's on the graph. Range means from the bottom to the top. Now, if I look at my graph, there's a, it's up here in the top, but there's nothing down here in the bottom. So I don't have all real numbers because there's no bottom. The lowest that my graph is going to go is right here. Oops. Right here. And so the y value, the lowest y it's ever going to go is -1. So everything above that, and so we use the symbol greater than or equal to, anything above the number -1 is going to be on my graph, but anything below the number -1 is not going to exist on my graph. So all of quadratics can really be done using Desmos. It can be done just by kind of reading your graph. Some of the things that we did talk about were transformations that involved changing my graph. So we had 3 places that we looked. We looked at the front number, we looked at this H, and we looked at this K. Your K value, your H value, I'm sorry, your H value is a liar. So for example, this one looks positive, but instead of going to the right, it goes to the left. So that's why we say H is a liar. In this one, it looks negative. So it looks like it's supposed to go to the left, but instead it goes to the right. However, K is kind. This K is positive, and it really did move up. When K is negative, it really does move down. So H is a liar, and K is kind. Then we have reflections and stretches and compresses. So we know that if A is negative, your first number is negative, that means that that graph has been reflected across the x-axis. We've also talked about what happens when you have a stretch or a compression, and we referred to these as skinny and chunky. So if your graph is skinny, it's been stretched, and if it's chunky, it's been compressed. And you can know that by the fraction. If the bigger number is on top, so for example, 4/3, it's skinny, and if the bigger number's on the bottom, it's chunky. So all I want to do is kind of go through these and just talk about what happened. So I have 3 areas that I need to look at. I need to look at my A value, my H value, and my K value. I do not have an A value, so it's not been reflected, it's not been stretched, it's not been compressed, but I do have an H value. I have an H value of 5, and so visually it looks like it's supposed to go to the right, but it is a liar, and so we're going to move to the left 5, but K is very kind. It's positive, and it will tell you the truth, so it really did move up 3. If I want to know the vertex, kind of where is this graph going to turn around, it's located at these values here. So it's located, it's an order pair, and it's located at -5, +3. If we looked at another one, we have 3 areas that we're looking at. We're looking at the front number, an H, and a K. So if I look at my red value, I've got 2 things. I know I've got a negative, so it's definitely been reflected. I also have the number 2, which as a fraction is 2 over 1. So this fraction is what I would call top heavy, which means that it's skinny. And skinny graphs have been stretched by a factor of 2. My H value is a liar. So it looks negative, like -4. It looks like it's supposed to go to the left 4, but it is a liar. So instead of moving to the left, it went to the right. And I have no K value, so the graph did not move up. The graph did not move down. In an example like 32, I'm going to look in those same 3 places. I'm going to look in my red zone, my blue zone, and my green zone. Now with this fraction, I can see that it is bottom heavy, which means that it's chunky. And chunky graphs have been compressed. I have an H value. H is a liar, so this one has actually moved to the left 1. K is kind, so we really did move down 4. If I wanted to know the vertex, where's the vertex? You can do one of 2 things. You can graph it, or you can just look at your H's and K's. So not +1, but -1 and -4. If we wanted to move backwards, we could move backwards. So it said, hey, can you fix the equation x squared to match all of this that's going on up here? So translated 3 units to the right and then 2 units up. So that's an H and a K. So remember, in our equations, H's are liars. So instead of going to the right, it's going to look like it's going to go to the left 3. K is kind, so we really are moving up 2. I don't have a reflection or a stretch or compress, so this is all I've got. The same can be done for something like this. You're taking your parent function and you're going to look for those keywords. So this one says vertically stretched, which means the graph is skinny by a factor of 4, and then translated 5 units down, which is a K value. So here it is a stretch. So my fraction 4 needs to be top heavy. So I can put all whole numbers over 1. So I can be stretched by 4. I don't have an H value, so you could put +0 if you wanted. And then 5 units down is -5. You might see it written like this. Y is equal to 4 x squared, because we have no H, minus 5. If I wanted to reflect it, number 35 does talk about a reflection, and then translated 7 units to the left, and then 1 unit down. I'm sorry, 1 unit up. So if I had to take my same parent function and modify it, I would say, well, a reflection means it's negative. There's no stretch or compress. 7 units to the left. Negative sign would represent left, but it's a liar, so we change it to positive. And K is kind, so I really will move it up. The rest of these can be found or solved using Desmos. So solutions to a quadratic equation are the points on which the parabola touches the x-axis. We like to set them equal to 0, but if you wanted to, you could just do what we've been doing in terms of graphing these, where you split them where the equal sign is. You have y equals the left and y equals the right. So if I pull up a Desmos, you shrink this down just a bit. There we go. If I wanted to use my Desmos, I could come in here and say y is equal to x squared plus 8x, and y is equal to 0, and then see where those two graphs intersect. So where the red intersects with the blue, there's where my intersection happens. And so if I wanted my solutions would be -8 and 0. You could do the same thing if it doesn't equal 0. You have one of two options. You can either set it equal to 0 and graph it like we did, or we can simply solve it going straight to Desmos where your equal sign is at. So where you have y equals the first and y equals the second. You can set it up. Y is equal to 4x squared. Y is equal to 10x. You have a red graph and a blue graph on mine, and I can see that they intersect twice. So I'd come in here, see where they intersect the first time, so when x is 0, and then find where they intersect the second time. That's 2.5. And so I would come in here and say x is equal to 0 or x is equal to 2.5. And so you can use Desmos to solve them. You can use Desmos to solve them no matter what they look like. So if they have multiple terms, you just find your equal sign right here and split it up. So then you can come right in Desmos and say, okay, same process, y equals 4x squared. Ooh, Lord Jesus, take the wheel. 4x squared minus 43, and y is equal to 6. And I can see that they cross at those 2 points, and that's x is equal to -3.5 and x is equal to 3.5. If I'm taking a test and on my exam there's fractions as answer choices, I would just put my fractions in Desmos or my calculator and see what does that look like as a decimal, and then compare your answer choices from there. I do want to take a look at one of our projectile motion questions. So a toy rocket's launched. They gave you the equation. So y equals -16. I'm going to change my t's to x's. Plus 32x plus 48. So here's my graph of whatever toy rocket this is. Down here, I'm going to put in right where you have your 0. This is like ground level. So the ground is down here at the bottom in blue, and the toy rocket went all the way up and then came all the way back down. It's asking what's the rocket's height at 2 seconds. So this is a really important kind of concept for us to look at, because this is in reference of height at a certain time. So height is your y, but time is your x. And this is saying, what is my y value when my time is 2 seconds? So the reason I like these kinds of questions is instead of doing a lot of math, I can come right in here and say, okay, if I want to look at my graph, here's my rocket. I want to know at what point is my rocket when my time is 2 seconds. So I can graph it and see, okay, this green line represents 2 seconds. And so the rocket, when it touches the 2-second mark, is at exactly 48 feet in the air. And you can do that for any kinds of questions that ask about height. But the one that I really, really want to spend a lot of time on is a question like question number 54. So 54 is a question involving regression. Our project is going to be on regression. You're going to have maybe 1 or 2 questions on your test. So I want to walk you through how to do this. Anytime you see a table in in your test, you need to recreate that table. So go plus table, and I'm just going to enter in the same values that are in my table into my Desmos. So 384. once you have your values in your table, if you hit that little magnifying glass in the blue section, it will take you to where all of your points are. And so you can see the curve that's happening here. And what we're going to need to do is create a model that connects these dots as best as possible. So if you open up a new section in your Desmos, you want to type this in exactly like I say it. Y1, so that's going to pull the Y values from your table. And in your keyboard, you're going to look for this tilde button. It's like a little squiggly spaghetti noodle. AX1. So that's going to pull from your table. And then we want to square that. So I'm just going to hit the square button. Plus BX1 plus C. So we're going to create an equation that looks, that's going to connect the dots that's written in standard form. So like AX squared plus BX plus C. We've got them connected. So now you can see, your 4 dots of data, but then what happens before and what happens after the data has been collected. So we only get these 4 dots. That's all you get, or 5 dots. That's all you get. But when we run regression, you can see beyond what those 5 dots tell you. So you can see all kinds of information. The other thing that you can see is it gives you your equation down here. So one of the questions that we were asked is, let me see if I can move this over just a little bit, to find the curve of best fit. Well, the curve of best fit is just the equation that Desmos is going to give us. So it gave me, for my A value, it gave me -16. For my B value, it gave me a 0, so I could put 0x. And for my C value, it gave me 384. So this is the curve of best fit that matches those points on your graph. With that, you can go in and you can evaluate anything at a certain time, at a certain height. This particular question is, find the time it will take for the hammer to reach the ground. So if I'm in Desmos, I do know that ground level is kind of where my x-axis is. So I'm just going to follow my graph all the way down until it hits the ground. So we're going, and it hits the ground right here, and Desmos has already plotted a point. So how long will it take in seconds for that toy rocket to hit the ground? Well, it's going to take 4.9 seconds. So all we had to do is connect the dots.